How's it going, ladies and gentlemen? Mr. Donahue here again. This time we're going to take a look at some practice problems for 14.4, the change of concentration with time. So our objective is to determine how much reactant or product remains or was produced for the first and second order reactions over time, and to use the rate loss to determine the half-life of first and second order reactions. All right, number one, under constant conditions, the half-life of a first-order reaction is unchanging. Yes, that is a true statement. Half-life doesn't change for first-order reactions. It's always constant. So let's keep reading. B, is the time necessary for the reactant concentration to drop to half its original value? That is the definition of the half-life. All right, C, can be calculated from the reaction rate constant. This is also a true statement. And what about D? Does not depend on the initial concentration of reactants for first order. That is absolutely a true statement. So it looks like E, all of the above, will be our answer. All right, number two, the following reaction is second order. There's the equation. At a given temperature, NO2 concentration drops from 0.200 molar to 0.0035 molar in 100 seconds. What is the rate constant for this reaction? So since it's second order, it's telling us that we have to use the 1 over AT equals KT plus 1 over A0 equation. So that's the one we're going to start with, and they're asking us to solve for K. So let's get that by itself. We're going to have to do 1 over the amount at some time minus 1 over the starting amount, and then that's going to give us KT. If I want K by itself, I got to divide each side by T. That cancels out. So now I can simply plug and chug. I have 1 over the amount at some time, which is this 0.00350. So 1 divided by 0.00350 minus 1 over the starting amount, which is 0.0200, all divided by 100 seconds. So when I do that, and I pick up my handy dandy calculator, beep bop, boop, I end up with 2.36 per molar per second. And there you go. Number three, the following reaction is first order. At a given temperature, K is this number. If the concentration of the reactant is 2.0 times 10 to the minus 3 initially, what is it after 1.00 times 10 to the 2 seconds? All right, so we got a time. We have an amount that we started with, and they're asking us, oh, hey, they also gave us the K. So first order reaction, the equation is the natural log of the amount at some time has to equal negative KT plus the natural log of the starting amount. So in this one, we're trying to get AT. So the way we get rid of the natural log is we put the whole other side to the base of E. So we're going to end up with the amount at some time equals that Euler's number, E to the negative KT plus the ln of A0. So now, well, let's see, they gave us K, they gave us T, they gave us the amount that we started with. So now we can just plug and chug. So we got E to the negative 5.91 times 10 to the minus 4 per second times the time of 1.00 times, another 0 times 10 to the second seconds plus the natural log of the amount that we started with. And the amount that we started with is that 2.00 times 10 to the minus 3 molar. So when I plug and chug, this is a good point for like a graphing calculator. You end up with 1.89 times 10 to the minus 3 molar. So that's it. That's how you do that problem. All right, number four, a compound decomposes by a first order process. What is the half-life if 25% of it decomposes after 30 minutes? So let me get a little chart here. The amount that I started with, if I'm dealing with percentages, is 100%. And it tells me that 25% of it decomposes. So the amount at some time is 75%. And my time is 30 minutes. All right. Now they tell me it's first order, so that tells me I'm going to have to use this natural log of the amount at some time has to equal negative KT plus the natural log of the amount that I started with. Now if I'm dealing with half-lives, it's helpful to remember this equation, that K is equal to 0.693 divided by the half-life. Right, in the instructional video, I go over how we can go from this equation to get this You just plug in, hey, at 1 half-life, these are the numbers you get, percentages wise. But, you know, if you could just remember this, you can go, hey, let me plug this in for anywhere there is k. So I have my new equation, natural log the amount at some time equals negative, well, hey, k is 0.693 divided by t1 half, so 0.693 divided by t1 half times time plus the natural log at the beginning, the starting amount. So I'm trying to get t1 half by itself. They're asking me for the half-life. So let me do some math. I gotta subtract each side, natural log the starting amount from each side. So I end up with ln of at minus the natural log of a0 equals negative 0.693 over t1 half times t. So now I want t1 half out of the denominator. So I'm going to move it to the top over there. I'm going to times each side by t1 half. And I'm also going to divide each side by this natural log of at minus natural log of a0. So I end up with t1 half equals negative 0.693 times time divided by ln of at minus ln of a0. All right, so now I can just plug and chug those values in. I got t is 30 minutes. The amount at a given time is 75%, and the amount that I started with is 100%. And when I plug and chug that in, I end up with 72.3, and the units that I used for time were minutes, so my half-life is that. All right, number 5, what is the reaction rate constant for first order reaction that has a half-life of this? So again, if you remember the first order reaction rate equation, you can work through it and you go, all right, well, at 1 half-life, what is the reaction? Basically, we're saying, you know, ln of 50%, let's say 1 half-life went by, equals negative k time, I don't know why I did 5, k times t1 half plus the natural log of 100%. And when you do that and you solve for k, you end up with k equals 0.693 over t1 half. Now I can just plug that in. 0.693 divided by 534 seconds, and you end up with 0.00130 per second as your K. All right, 6. A second order reaction has a half-life of 21 minutes when the initial concentration of the reactant is this. The rate constant for this reaction is what? So second order reaction, 1 over the amount at some time has to equal K times T plus 1 over the starting amount. Right, so now if I wanted to work through this again, I can go, all right, well, at 1 half-life, I have 1 over 50% equals KT plus 1 over 100%. You know, so I go, all right, well, let me do some math, and I get 1 over 50% minus 1 over 100% equals K times T. Now, these 100%, I'm just going to say, hey, that is all of my starting amount. And 50%, well, it's 50% of my starting amount. So now when I do some algebra and solve for K, I end up with an equation that looks like this. K equals 1 over whatever the starting concentration was times T1 half. So now I can plug and chug. They told me the half-life is 20 minutes. That's my initial concentration. So let me plug and chug. Oh, wait a minute. Problem here. They want it in molar per second and they give me minutes. So I got to go, hey, 21 minutes times 60 seconds equals my time, right? So K equals 1 over my initial concentration of 0.6 molar times 21 times 60. Give me my seconds. When I plug and chug and get that answer, I end up with 0.00132 molar to the minus 1, seconds to the minus 1. All right. 7. The decomposition N2O5 dissolved in carbon tetrachloride follows this reaction. There it is. It's a first order and has a rate constant of that number at a given temperature. If the reaction started with this many moles in a 1 liter vessel, how many moles are left after 175 seconds? So this is my K, this is my A0, and what they're trying to ask you for is, well, how much is left after that time? First order tells me you got natural log of AT equals negative KT plus natural log of A0. And I'm trying to solve for AT. So I got to put the other side to the base E. It's E to the negative KT plus ln of A0. So now I should be able to plug and chug. What's nice about the concentration is it's in a 1 liter vessel. So this 0.081 moles is 0.081 molar, right? So E to the negative 5.02 times 10 to the minus 3 per second times 175 seconds plus the natural log of what I started with, 0.0821 molar, I'm sorry, 81 molar. Just add numbers in. And now I pick up my handy dandy calculator and I beep bop, boop, and I get 0.034 molar when I round it to the correct number of sig figs. Right, number 8, the elementary reaction below is a second order in terms of NO2, and the rate constant at a given temperature is this. There's the equation. What is its half-life when the initial concentration is this? So again, we go, hey, second order, maybe I already remember that my T1 half equals 1 over my initial concentration times my K. If not, you can work through it. You go, hey, it's 1 over AT equals KT plus 1 over A0, and then at 1 half-life, you know that AT equals 0.5 of A0, and you can plug and chug and rearrange, and eventually you get this equation. It might be easier to remember than work through, but you could always work through it and get it. So now you go, all right, well, let me plug and chug. 1 over initial concentration of 0.56 molar times the constant of 9.63 times 10 to the minus 3 molar to the minus 1, second to the minus 1. All right, so then when I plug and chug, I get to 2 sig figs, 190 seconds. All right, number 9. A second order reaction has a rate constant of this. If the concentration of the reactant is initially 0.3 molar, how long would it take for the concentration to decrease to 0.09 molar? So again, second order, we got 1 over AT equals KT plus 1 over A0, and they're asking for time, right? So they gave us the K, they gave us the amount that we started with, they gave us the amount that they want to end up with. We're solving for T. Well, let me do a little rearrangement. I do 1 over AT. Well, let me subtract 1 over A0 from each side. That's going to equal KT. And I'm trying to get T by itself. I don't know why I drew that T tiny. It's a tiny T. So divide each side by K. K cancels out, and there we go. We got the equation for time. So time equals 1 over the amount at a given time, so 0.090 molar, minus 1 over the original amount, 0.30 molar, all over my K of 0.74 molar to the minus 1, second to the minus 1. So when I plug and chug, I end up with, rounding to 2 sig figs, 11 seconds. So there you go. Take 11 seconds for that to happen. All right, I hope you found it helpful. See you in class. Goodbye.